Hello guys, welcome back to my YouTube channel. This is Nehati from Sri Venkateswara College of Engineering, and today I'm here with a video on multi-threading from operating system. So let's see what we have in this video. First, we'll be saying about threads. That is the introduction part of threads. What is thread? After that, we'll be seeing the two types of thread, that is user level threads and the kernel level threads. Then we'll go to multi-threading. After that, the types of multi-threading. There are three types in multi-threading: many to many, one to one, and many to one. And then we'll be concluding with the conclusion. So, first of all, what are threads? A thread is a single sequence stream within a process. So threads are also called lightweight processes as they process some of the properties of process. So a thread basically process the properties of a process, and hence they are called lightweight process. Each thread belongs to exactly one process. One thread has exactly one process. In an operating system that supports multi-threading, the process can consist of many threads. The process consisting of many threads is known as multi-threading. So after this, we'll see what is user level threads. First of all, what is user level threads? The user level threads are implemented by the users and kernel is not aware of the existence of these threads. So basically, user level threads are created by the users, they are implemented and managed by the user, and kernel has no awareness, or the kernel doesn't have any idea about the existence of these user level threads. They are managed by the user library and hence is faster than the kernel level threads. Since the user level threads are managed by the users themselves, it is faster compared to the kernel level threads. Then they are represented by a program counter, stack, register, and small process control block. We can see that in the diagram. Also, there's no kernel involvement in synchronization for user level threads. As I said, kernel level threads, the kernel has no idea about the user level threads, and so there is no kernel involvement in the synchronization for the user level threads. So kernel level threads are handled by operating system directly. If user level threads are managed and handled by the users, kernel level thread is managed by the operating system directly, and the thread management is done by the kernel. The context information for the process as well as the process thread is all managed by the kernel, and hence we say that kernel level threads are slower than compared to the user level thread. Because of this, kernel level threads are slower than the user level thread. If the kernel level threads are blocked, it doesn't affect any other threads. So about this, we'll be saying in the later slides. So coming to multi-threading, multi-threading allows the application to divide its task into individual threads. So in multi-threading, there will be many threads, more than one thread, and hence any task that the threads get can be divided into divided and given to each thread, making it more easier to complete the task, and it makes the completion of the task more quicker. So with the use of multi-threading, multitasking can be achieved. This is what I said. And in multi-threads, the same process or task can be done by a number of threads, making it easier to complete the task easily. Okay. So types of multi-threading, we have one to one, and many to many models. So the first one is the many to one model. In this model, we have multiple users. So the first word refers to the how many user threads we have, and the second refers to the number of kernel threads. So many to one in the sense there will be many user level threads and just one kernel level thread. In this model, we have multiple user threads mapped to one kernel thread. Here, when a user thread makes a blocking system call, the entire process blocks. Because since we have only one kernel thread, if any user threads makes a blocking system call, the entire process blocks. As we have only one kernel thread, only one user thread can access the kernel at a time. So multiple threads are not able to access the multiprocessor at the same time. The thread management is done on the user level, so it's more efficient. If since we have only one kernel, each user thread has a particular time to access the kernel level thread. All the threads together cannot access the kernel level thread. This is what we have in this many to one model. Coming to one model. In this model, there is one-to-one relationship. For one user thread, we have one kernel. So in this model, multiple thread can run on multiprocessor because every user thread has its own kernel thread. Problem with this model is that creating a user thread requires a corresponding kernel thread. So if we have a user thread, if we're creating a user thread, we should make sure that that user thread has a separate kernel. So as each user thread is connected to different kernel, if any user thread makes a blocking call, it doesn't affect the other user threads or other kernels. If one user thread is making a system blocking system call, it affects only that particular kernel and user thread. The other threads are not affected at all in this one-to-one model. Coming to many model, in this model we have multiple user thread, multiplex, or to same or lesser number of kernel level threads. So in this many to many model, even though there are more than one thread, user threads or more than one kernel thread, the main point is that the user level threads are more compared to the kernel threads, more or equal to the kernel threads. So number of kernel level threads are specific to the machine. The advantage of this model is if a user thread is blocked, we can schedule other user threads to other kernel thread. So if user thread one makes a system blocking system call, we can schedule that user level thread to another kernel level thread. That is what we have in this many to many model. So, coming to the conclusion for this video, although multi-threading offers several advantages like multitasking, it has its own share of drawbacks too. For example, multi-threading creates the context switching overhead. It requires thread or process support. It requires careful synchronization of threads. Sometimes it may consume large space due to the block threads, etc. So basically, this is all about multi-threading. In a short time, I've tried to complete how much I can. So thank you all for spending your time over here. Thank you for watching my video. Please do not forget to share, like, share, and subscribe. Thank you so much.